Welcome to this webinar on silicon photonics, grating coupler design and optimization. My name is James Pond and I'm the CTO of Lumerical, and I'll be giving this webinar today. So we have quite a few things to cover. First of all, I'd like to give a brief introduction to Lumerical and then an introduction to grating couplers, talk a little bit about the motivation behind grating couplers and some of the basic physics of operation. Then we'll talk about the design methodology and parameterization, look at some of the key performance metrics and consider design optimization. Finally, we'll characterize the grating couplers by an S-parameter matrix for inclusion in larger scale circuit simulations, and in so doing we'll be able to look at the impact of the grating coupler performance on the overall circuit performance, and then we'll have a chance for questions and answers. So about Lumerical and our technology. We have four products. The first one I want to talk about is Mode Solutions. Mode Solutions has an eigenmode solver which can solve for waveguides and fibers of arbitrary cross-section, like this photonic crystal fiber. And since Mode Solutions 5.0, we've also added an omnidirectional propagator, a 2.5D propagator, which allows for omnidirectional propagation within a plane. And it's ideally suited for silicon photonics or integrated optical problems. It can solve things like this ring resonator very quickly and efficiently. And as we're going to see in the webinar today, we're actually going to use this to design a portion of the grating coupler. Then FTTD Solutions is our fully vectorial 3D Maxwell solver, which can solve for arbitrarily complex geometries for structures like the CMOS image sensor that's shown here. With FTTD Solutions, we're typically looking at near-field results. We may also want to do near to far-field projections to look at angular distributions of radiation. We may want to do things like in the CMOS example where we are looking at the optical generation rate, or looking at where and how many photons are converted into electrons and holes in the silicon, and so on. This year, in early 2012, we added Interconnect, which is a photonic integrated circuit simulator, and it allows to simulate circuits at a higher level of abstraction, more similar in concept to SPICE modeling for electrical circuits. And so this allows us to look at very, very large circuits and systems and to look at their overall performance in terms of S parameters and also in terms of signal integrity analysis in the time domain, looking at things like eye diagrams. And then Device, also added in 2012, about 5 months ago, is an electrical solver which allows us to solve for the electrical properties of devices. And so it's often used in conjunction with FTTD Solutions or Mode Solutions in order to solve for devices like CMOS image sensors, solar cells, high-speed photo detectors for silicon photonics applications, and also Mach-Zehnder modulators. In terms of our customer base, we serve a large number of well-known research and development companies around the world, and this makes it very interesting to work at Lumerical because we have the opportunity to stay in touch with some of the leading-edge commercial research and development as it's happening. And in fact, we serve a wide variety of applications and market segments. And this speaks to a large extent to the versatility of our software, that it can address so many different applications. Of course, today in the webinar, we'll be focused on silicon photonics and in particular the grating coupler component. We also, in addition to our commercial customers, have a large number of academic customers around the world. And this, again, gives us the opportunity to stay in touch with some of the more maybe blue sky leading edge research that's happening at different academic institutions. And in total, we serve hundreds of different organizations in more than 30 different countries. And since Lumerical's creation in 2003, our technology has become well proven and very trusted in the industry. The number of patents and publications that reference our software is growing at more than 70% per year, and now there's well over 1,000 patents and publications referencing our software tools. So now I want to talk specifically about grating couplers and a little bit about the motivation for them. Grating couplers are an alternative to end-fire coupling. On the figure on the left here, what you can see is sort of an end-fire coupling scenario where you can bring a beam, or in this case a fiber, right up to the edge of a cleaved chip and therefore couple light into a waveguide. And end-fire coupling has some advantages. It can be very low loss, and it can actually operate in a very broadband way with low insertion loss. But of course, one of the disadvantages is that you do have to cleave the chip, and this sort of limits the number of places on the chip where you can actually bring light on or off. The grating coupler gives you the opportunity to do vertical coupling of light, and therefore you can have a beam that comes in from above, or you can extract light vertically out of the chip. You can also use a fiber and have a fiber almost like a light contact for the fiber at any position within the chip. So there are many advantages obviously to that in terms of the fabrication process and the number of places you can bring light on and off the chip. The downside of grating couplers is that as we're going to see, there's always a more limited bandwidth that's available, and the coupling efficiency is always a challenge. So in order to solve those problems, we need some good design tools to be able to choose the optimal design parameters. And I also want to bring up, in terms of motivation, a couple of slides that were given to us courtesy of Dr. Michael Hochberg, who's the director of OPSIS. And these slides come from a presentation we gave a couple of weeks ago on silicon photonics more generally. But it's really interesting to look at where grating couplers appear in these slides. And in particular, this slide is about the commercialization of silicon photonics, and Luxtera is actively commercializing silicon photonics product, a 40 gigabit point-to-point link. And if you look in the screenshot here, you'll see that grating couplers do appear, in addition, of course, to the waveguides and ring resonators. If we look in a little bit closer at this device, you can see that obviously we're using the silicon waveguide and SOI. There's a ring resonator, a sort of classic device for filtering in silicon photonics. But over here is where you see a grating coupler being used. And so grating couplers are not just sort of something of research interest. They're being actively commercialized now. In terms of the physics of operation, the grating coupler actually is a relatively simple thing in concept. Basically, we're looking at scattering of light from a periodic grating, from a periodic structure. And so if you have light that's incoming through this slab waveguide that's incident on this periodic grating, each unit cell of the grating will scatter light. And of course, we can write down a simple Bragg condition for the angles where we're going to get constructive interference of that light. So this is something almost like a first-year physics problem where we can add up the optical path length of the light as it travels through the structure and scatters. And what we want to make sure of is that, or where we will have light emission is at angles where we have an optical path length for each unit cell that varies by an integer fraction of the wavelength. And so we can write down a simple condition like this that tells us what the angles of emission will be as a function of the effective index of the waveguide, the cladding index above the waveguide, the wavelength, and the pitch of the grating coupler. And of course, there's a integer m in here, which in principle can take on any value. So there are a few kind of key points. First of all, we typically don't want to send out light at many different angles, and so we deliberately choose m to be 1 and have the pitch to be small enough that we only support one diffracted order from this device. So we only get out light at one particular angle, and that means that the pitch is going to be something that's sub-wavelength. Also, the other thing to note is that there's a linear dependence of the angle on the wavelength. And this is really one of the factors that limits us in terms of bandwidth, because as the wavelength changes, our angle of emission changes, and this will change our ability to couple light into or out of a fiber that's coming in at a particular angle. Now, in terms of the simulation and design methodology, we're going to start with a very simple back-of-the-envelope design that uses the information from the eigenmode solver and mode solutions. And the information we really need is that effective index. Then we're going to move on to grading parameter simulation and optimization with 2D FDTD, and we'll also take a practice at S parameter extraction. From there, we can look at taper optimization with the 2.5D propagator and mode solutions. Then we're going to put the results of all that together into a 3D FDTD simulation and look at S parameter extraction from the actual full three-dimensional device of the grading and the taper section. Once we have that, we can do the simulation and interconnect, and we're going to look at something really simple, which is two grating couplers connected by a waveguide, so we can get light in and then back off of a chip, and we'll see how some of the performance issues, in particular the reflections of the grating coupler, will affect the performance of even such a simple device as that. So in terms of the initial design with the eigenmode solver, we're just going to start out with some of these parameters. So we'll assume that the cladding region has an index of 1.45. Now, in terms of the effective index, we're going to use sort of an average value. This is a really back-of-the-envelope type of approximation. The problem is that when we look at one unit cell and we're trying to look at the effective index of the slab, of course we have two different regions here. We have a region where the slab is thicker and a region where the slab is thinner. And so if we calculate the effective index of the slab modes in both regions, we'll find something that varies from 2.85 in the thick region to 2.34 in the thin. We can average those two and say that our effective index is going to be approximately 2.6. And this is definitely back of the envelope, but it does represent reasonably well the amount of phase that will be accumulated as light propagates through one unit cell. I should say that there are situations where you may etch your grading all the way down to the oxide, and in that case it's not clear what you should use for this region here, but if that were the case, I would simply use the cladding index at that point as a reasonable approximation and average the effective index between the thicker slab and the cladding index. We're going to use a wavelength of 1.55 microns as our center wavelength of operation. And we want to have an angle of 13.45 degrees, so we want to be a little bit off normal incidence. And if we take our Bragg condition that I showed earlier and just rewrite it to solve for the pitch, then what we find is that we want to have a pitch of 685 nanometers to have this device operate the way we want. So that's what we're going to start with in our initial design, is that pitch. And I should say, I didn't mention, but we started out with a waveguide thickness of 220 nanometers and then an etch depth of 100 nanometers. So the thickness in here is 120 nanometers. So now we can take a look at our structure in 2D FDTD simulation and run the simulation of it. And I'm going to show a demonstration of that. So here's the structure shown up in 2D FDTD. And you can see the grading itself. And initially what we have is a source that's a slab mode source that's going to inject light in the fundamental mode of the slab, and then the light will be outcoupled by the grading here. So I'm just going to run this simulation. And the nice thing about 2D FDTD, of course, is that it only takes a few seconds to run a simulation like this. And we can look at the light that is immediately above the surface of the grating here. So if I wanted to visualize, for example, the electromagnetic field, I can do it like this, and I could look at the field at a particular wavelength here, and you see that there's a lot of oscillation, and the field is sort of decaying as it travels through the grating. It's much more interesting to look actually at the far field projection and look at the angular distribution of the emission, as well as the total power that's transmitted out of the grating. So maybe initially we'll take a look at the total power as a function of wavelength, and here's where we see something that is outcoupling about 60 to 65% of the light from 1.5 to 1.6 microns, which is a bandwidth that we're working with here. And you see that it's actually relatively flat across that range, but now let's take a look at the far field, and we'll see why we're going to be ultimately limited in our bandwidth. So to look at the far field, I just have to calculate the far field projection, and I'm going to do it at all wavelengths. And this image here shows you the electric field intensity is a function of angle and wavelength. And when you look on this image, you can see the linear dependence of the angle with the wavelength. So let me just take a plot, a one-dimensional cross-section through this now, and we can look at different wavelength values. And so what we see here is the angular emission at a wavelength of 1.5 microns, and as I move this up to a wavelength of 1.6 microns, we see that the peak angle of emission is changing. And in fact, at 1.6, our angle of emission is somewhere around 10 degrees, and at 1.5, our angle of emission is way up at 18 to 19 degrees. So we have an almost 10-degree shift in angle of emission, just over from 1.5 to 1.6 microns. And at 1.55, which is the design wavelength here, we can see that our angle of emission is about 14.7 degrees, and that's actually remarkably close to the 13.45 degrees that we designed for using the simple back-of-the-envelope calculation. So that calculation is still a remarkably good starting point for our design. Now, of course, that shows you the output. We may also want to try running this in input mode, so we could disable our waveguide source and enable a beam that's coming in at the 13.45 degrees. And if we run this simulation, this now gives us the opportunity to look at the light that is coupled into the waveguide mode. So first of all, I can show you the transmission through this surface here. So if I visualize that transmission, you'll notice it's negative, and that's because the power is flowing down the negative x-axis. I just want to reverse the sign on that. And so here we see something where we actually get a reasonable input coupling efficiency, almost 50%. Not quite centered at the 1.55 that we were anticipating, but it's still very close to that. And the question you may be wondering, though, is all of this power that we're counting here actually propagating in the fundamental mode of this slab, or is it scattered down and traveling in the oxide or above in the cladding? And we can answer that question by looking at this modal expansion monitor, which will actually expand the fields onto the fundamental mode, and so we can determine what fraction of the power is actually propagating in the fundamental mode. So we can compare the forward power, the total power, which is what we just saw. Again, I have to reverse the sign on these two quantities. And here we see that the power is almost all of it is actually propagating in the fundamental mode at the point where we've measured it here. So there's only a very small fraction of the power that's not propagating in the fundamental mode. So we are actually achieving a coupling efficiency of close to 50% here at the peak into the fundamental mode. So I've shown, what I've shown here is some of these far field images and the angular emission, and also looked at the reversed simulation where we can see that most of our power that we're accounting for here is actually propagating in the fundamental mode. Now, what we want to do next is take a look at fiber coupling, and I'm going to show a demonstration of this in a moment, and we're actually going to consider fiber coupling from here on. Before I show the demonstration of that, I just want to talk a little bit about parameterization of something like this type of design, because the grating itself needs to be parameterized, and the fiber, as you can see here, also needs to be parameterized. And so we have a parameterization capability which allows you to do almost anything that you want. And in particular, you can construct objects like this grating coupler, which have properties which are appropriate for your device. So our grating coupler 2D structure has properties like etch depth and duty cycle and pitch and so on. And then we can simply modify these properties and have the grating coupler structure recreate itself with the desired parameters. And in fact, you can parameterize any group because the group can set the properties of its children. So even the fiber itself is actually parameterized. And the way that it works is you can, first of all, add in the variables that matter. So in this case, we have things like the core diameter, the cladding diameter, the angle, the core index, cladding index, and so on. And then behind that, there's a script which actually can modify the properties of all of the children according to the parameters that you want to set. So in this case, for example, the script can select the source and modify the angle and rotations and positions and so on. And we can also select the monitor above the structure and modify its position. Sorry, I moved ahead too quickly. So this allows us to align all of these different structures, rotate them, put them exactly where we want, rather than trying to do that by hand every time we want to change the angle by 1 degree. So doing this is really essential for reproducibility. Obviously, if you do everything with the mouse each time, it's very easy to make mistakes, and it also takes a long time to align everything. It makes parameter sweeps and optimizations very easy. Basically, it's a bit of work to get this started and get something fully parameterized, but once you've done that, everything else becomes incredibly easy, like parameter sweeps and optimization. And of course, you really only have to do this once for a particular design, and then you can continue to use that same structure again and again. You can cut and paste it into other files. So it's really worthwhile to do that. You can also download a lot of these preset designs directly from our component library, which is linked to our website and keeps a lot of these different components up to date. So you don't generally have to actually start creating these things completely from scratch, or you can often use ours or make small modifications to ours. And our hierarchical group layout and script-based parameterization does make almost anything possible, so it's certainly worth the initial investment. Now, also talking about optimization and parameter sweeps, generally when we're doing that, or almost by definition, we require many different simulations. And so what we'd like to do is be able to not just get each individual simulation running as quickly as possible, but actually get all of our simulations as a whole running as quickly as possible. And one really convenient way to do this, if you don't have access to a high-performance cluster, if you have access to a number of workstations on, say, an office network, which is quite slow, is to actually send out each individual simulation to a different workstation. And then each workstation can run, it may be running in a distributed computing mode using all of its internal cores and all of its internal processors, but you can be running, say, 10 simulations at the same time on 10 different computers, and that will get your optimization or parameter sweep done 10 times faster. And this works really nicely even on slow networks. So let me come and show some of the things that I've been talking about. So first of all, we can take a look at the fiber simulation. So let me disable this beam source and enable the fiber source here. And so now the fiber is shining into the grating coupler, and we're going to couple light into this waveguide. You notice the angle may look a little bit strange. I've disabled the automatic aspect ratio setting because the grating coupler is quite thin. So sometimes to the eye, the angles look a little bit strange, but you can always force a uniform aspect ratio and then see that the angle is in fact as expected. So I'll just run this simulation. And again, we can take a look, for example, at the power in the fundamental mode at this point here. And we see that, again, even with the fiber, like the beam, we're able to achieve approximately a 50% coupling efficiency into the fundamental mode of the slab. Now, in terms of optimization, just before I start, I'd like to come back to my notes and talk about what I'm going to do. What we'd like to do is get a grating coupler that has a broad bandwidth of operation and also has a very high coupling efficiency or low insertion loss. So in order to do that, we're going to define a figure of merit, which is the average transmission from 1.5 to 1.6 microns. So we're just going to take the transmission at each wavelength, integrate over this whole range, 1.5 to 1.6 microns, and create an average value of transmission. And then once we've done that, and I created that figure of merit as one of the default calculations, then it's very easy to, for example, sweep the source position. So we're going to do a sweep where we move the source position over a range of values, about 10 simulations, and we're going to see if we can find an optimal alignment of the source with the grating coupler for best coupling efficiency. So let me just run this sweep here. And the way it's working is that it first saves 10 files, actually 11 files, the number of points in my sweep. So it's saving 11 different files with different positions of the fiber. And once those files are saved, it now starts launching those simulations on 4 computers that I've added to my resources. So we've got 4 computers working away on this problem, and that allows me to get through all 11 simulations in just a few seconds. And once the simulations are complete, we now reload all of those files and extract that average transmission from them. And that way we can actually calculate the average transmission. So let me just visualize that result. So here is the average transmission as a function of position, and you can see that we clearly have a peak average transmission when the fiber is aligned at 3 microns with respect to the grating edge here. So we found our optimal fiber alignment, and now let's suppose we wanted to move on towards optimizing this design. And the easiest things, maybe from a manufacturing point of view, that we can vary are the pitch and the duty cycle of this grating. So I've created an optimization task here, and this optimization task will allow us to vary 2 things. Or it will try to optimize based on 2 parameters. It'll optimize based on the pitch and the duty cycle. And of course, the figure of merit that it's going to use is this average transmission that I already talked about. And this optimization algorithm is going to use particle swarm optimization. So if I press run on this, it's going to do something a little bit similar to the parameter sweeps, but what it'll do is it'll save 10 designs with randomized pitch and duty cycle in the range that I have specified. And then when those first 10 simulations are completed, it'll start running them on the 4 workstations that I've made available for this. And once completed, it will load up that first generation of designs, and it will determine the best figure of merit that's been found. And then it goes into the next stage where, based on the results of the first generation, it will create a new generation of designs and run another set of 10 simulations. And so we can see actually our initial random selection already found quite a good solution where we're up to about a 37% average efficiency from 1.5 to 1.6 microns. Now we're into the second, we're just loading up the second generation of designs. And so we'll see, here's by the second generation, we've already jumped from 36 to about 39. And I know that that's actually very close to the optimal value. So I'm going to stop the optimization at this point. We'll see in just 2 generations, we got to 39.5% average coupling efficiency. Okay, and these are some results that I ran initially. So this initial design was a little bit not as close to optimal at 30% efficiency, but within a few generations we were up at something very close to the 40% efficiency that we just achieved there. And so the optimal parameters that we found here are 660 nanometers for the pitch, which is sort of remarkably only 25 nanometers away from the design that we had with the back of the envelope calculation. And we also found a duty cycle of 0.66. I should say that the duty cycle was not something that we could predict with the back of the envelope calculation, and so I just used a duty cycle of 0.5 initially, but it turns out that 0.66 is more optimal. And then this is the transmission that we can achieve with these parameters. So now we're going to talk a little bit about S-parameter extraction. So what we really want to do is treat this grating coupler as like a black box component with some S parameters. And the S parameters will tell us how much light is coupled into the waveguide and how much is reflected on input and also on output. It's important to remember that the S parameters are complex coefficients, so this is not just the power coupling efficiency, but it also is a measure of the phase of the coupling, and the phase can be very important for certain applications, of course. These are the results that we're going to find for our optimal design, and let me just show a demonstration of how this is calculated. So this actually involves two simulations. Because it's not a symmetric device on the input and the output. So what we need to do is to be able to run a simulation with the fiber in and measure the S parameters in, and then reverse that, have the waveguide mode and measure the S parameters on the way out. So I've got a script that does that, and it will actually calculate the it'll basically do these two calculations and collect the S parameter data. And not only will it collect it and visualize it, it'll also export it to file so we can use it later if desired in interconnect. So let me run this script. So now it's running the first simulation. Actually, maybe before I do that, I should say, well, I didn't actually set the optimal parameters. So here we're calculating the S parameters for the original parameters that I had, so I didn't set the pitch and duty cycle to the optimal parameters, but nonetheless you'll see how we can extract the S parameters, and I do have the results for the optimal design in the slide, so I can show you that in 1 second. Here we're calculating the modal expansion. The rotated mode fiber is quite a complex calculation, and so the modal expansion takes actually just about as long as the FTTD simulation itself. So here are the S parameters. Looking at the real and imaginary parts for S parameters doesn't make a lot of sense. It's better generally to look at the absolute value and the phase. And so here's the S parameters, and you see the peak value here at 1.56 or 1.56, which is because I used the original design, not the optimal design. However, if I had used the optimal design, you would see the S parameters centered at about 1.5 or close to 1.55 microns, and this actually gives us the best average coupling efficiency over the entire bandwidth that we're considering. But what you also notice is that we have quite a bit of reflection. So S11 and S22 are certainly not zero, and they're large enough that we're going to see some impact of that reflection in the performance of our grating couplers when we put two of them together. Okay, and also I didn't show the plot in the demonstration, but you can also look at the phase of the S parameters. The phase of these S parameters in these devices, because they're non-resonant devices, is basically a measure of the optical path length, and it's a pretty much a straight line with a slight exception on S11. That would certainly not be the case of a resonant device like a ring resonator. So now in terms of the 3D design, we've got a good starting point. We can use the pitch, duty cycle, and the fiber alignment that we determined from the 2D FTTD. We can use circular etch lines, and in using the circular etch lines, we can try to focus the light actually down into a waveguide here. And the remaining question is, what shape should we use for this tapering section? Should it just be straight? Should it be parabolic, or what? So one thing we can do is actually parameterize the design of this taper section. And so we can look at a few different shapes. So I parameterize this design with this fairly simple formula. The key thing is it's basically proportional to x to the power of some exponent. We can look at an exponent of 1/2, so it's basically a square root, or an exponent of 2 where we have something much more parabolic. And we can look at a variety of different values for this exponent m. Otherwise, we're constrained because at the input we have a fixed width, and at the output, of course, we have a fixed width which matches our waveguide width, which is a 500 nanometer wide waveguide. So to do this optimization, what I did was I started with a Gaussian slab, or a slab Gaussian beam in the Mode Solutions 2.5D propagator. And this propagator is really ideal for propagating light in slab modes like this. In fact, it has no approximations for this type of propagation. And so I created a beam that was focusing and of approximately the same diameter that we'll have coming out of the grating coupler. So this beam, even in a slab without a taper, is naturally focusing to a waist 25 microns away from where the beam is injected. So very similar to what we will get out of the three-dimensional grating coupler with the curved etch lines. And then we're going to run a parameter sweep to look at the transmission to the waveguide as a function of this exponent m. So you're seeing some results here, but let me actually show you a demo of how this works. Here's the design drawn up in Mode Solutions. So we see the taper design and the beam coming in. This beam again is naturally is focusing already to approximately the entrance to the waveguide here, and if we run this parameter sweep on the exponent m, you can see the different taper designs changing that we're going to be sampling here, from sort of very thin to much more parabolic, or even I think we go up to an exponent of 4 in this parameter sweep. So here I've obviously just got two computers set up in my resources, and they'll be running these. Now the great thing about the propagator simulations is that they're very fast. So this is maybe a 20 to 30 second simulation, even though we're simulating a region which is 40 or 30 to 40 microns by 20 microns. And so I'm not going to actually go to the end of this because it'll take a couple of minutes to finish the whole parameter sweep. Let me just stop this simulation and come back to the slides, and I can show you the results. So first of all, that first parameter sweep varied the exponent from 0.1 to 4, and we see quite a variation actually in the coupling efficiency. And then this peak value is actually somewhere close to 1, which is basically a linear taper. But when we run on a smaller range to get a little more precision, we find that the optimal design is 1.15, so a slightly nonlinear taper design. And actually there's a reasonable amount of sensitivity to the shape of this taper. So even varying m from 0.9 to 1.5, which is not a huge change visually, it actually does lead to a substantial change in the coupling efficiency into the waveguide. So we're going to stay with this design of m is 1.15 for the exponent. And now we're ready. Sorry, not quite ready. I should say I did that calculation just for one wavelength. This type of device, we're not expecting to see a substantial variation as a function of wavelength, but it is worth verifying. So I reran the calculation with m as 1.15 broadband from 1.5 to 1.6 microns. And so here's the actual transmission and how it varies. And so we're actually able to achieve almost a 90% coupling with this particular taper design into the waveguide mode by using this choice of M. So we are still obviously losing some of the light, but it's a relatively small amount. So now we can run the 3D simulation, and I'll show you a screenshot of this. I'm not going to run it in this webinar because it takes a few minutes, but to give you an idea of the times, I can run it on my laptop in about 60 minutes. That uses the 2 cores that I have available. If I run it on a better workstation, the simulation time is under 10 minutes. So this was 9 minutes on a 4-processor AMD workstation with 32 total cores, using all the cores. This workstation was purchased a couple of years ago, so it's not a state-of-the-art workstation. It's a very reasonable one, and even with that, we're getting the time down to under 10 minutes. I believe with a current workstation purchase this year, this would probably be closer to 5 minutes. And it's actually interesting that the calculation of the modal expansion of the fiber is actually the longest part of this. It takes about twice as long as the FTTD simulation. That's something we'll be working on optimizing for the future and improving. Nonetheless, this is a very particular case. We have a very large fiber mode that's rotated at an angle, and so that part of the modal expansion takes about 20 minutes. Nonetheless, when running it, we can extract the S parameters in exactly the same way that we did for the 2D simulation. And what's interesting to see is how similar the S parameters actually are between 2D and 3D. Overall, of course, we have a lower coupling efficiency in 3D, which is not unexpected, and one source of that obviously is that in 3D we included a taper section with about a 90% coupling efficiency, which was not included in the 2D simulation. But otherwise they look very similar, and we see a lot of the same features in reflection as well. So clearly we can do a lot of the design optimization in 2D where the simulations take 3 seconds rather than 3D where the simulations take 10 minutes. We can also look at the phase of the S parameters from 2D to 3D, and again we see that most of the features are actually relatively well represented. The slope of the phase is a little bit steeper in 3D, but that's really just an indication that we have included the longer taper section, so the optical path length through the device is longer in the 3D simulation than it was in the 2D simulation. I'll show just a screenshot of the three-dimensional simulation. So this is the three-dimensional grating coupler simulation, and you can see the fiber coming down above the structure here. And what we're calculating for the transmission on the input is the fraction of power which goes into the fundamental mode of this waveguide over here. And then, like 2D, we run a simulation where we reverse things. We've also taken advantage of the symmetry. You see this sort of green half of the simulation region, and that's where we use an anti-symmetric boundary, which is appropriate for this polarization in order to reduce our simulation volume by a factor of 2. Okay, so that's the FTTD and mode simulation. We now have our design. What if we want to actually start simulating how this grating coupler is going to perform in larger scale circuits? And that's where we turn to interconnect. So interconnect is a photonic integrated circuit simulator, and as you can see, it's not working at the physics level where we're solving Maxwell's equations directly. This is a more schematic representation of the circuit, and in this case what I've done is inserted some S parameter elements where I can read in the S parameters that we've extracted in our FTTD 3D FTTD calculation. And I've also put in a waveguide section where the waveguide parameters are extracted from mode solutions. So that means we have an accurate representation of the waveguide in terms of its effective index and also its group index, which is really key actually for many of these devices. So here we're going to see, and I'll show you in a minute, we actually have the mode profiles as well as that effective index and group index imported from mode solutions. And then the 3D FTTD results that I exported to file are used to define the S parameters in this for the grating couplers in the interconnect simulation. And then interconnect is a product that can actually operate in both the frequency domain and the time domain. Here the interesting thing is to use an optical network analyzer, which basically allows us to measure directly the S parameters of any size of circuit in the frequency domain, of course. So that's what we're going to use here. And let me show you an example of this running in interconnect. So here is the actual the circuit and the network analyzer, the S parameters, and so on. I'm just going to hit run on this, and the simulations in interconnect are obviously very quick. It's just a few seconds to simulate a couple thousand points in different wavelengths. We can look at, for example, the mode profile. This is the mode that was imported from mode solutions. When I first open it, of course, the axes don't happen to be set up to plot very well. This should actually be plotted in the Z plane, and that's where we can actually see the mode profile imported from Mode Solutions quite clearly. And this mode profile is, of course, a function of wavelength. So while there's not a lot of variation as a function of wavelength, there is some. But what we're really interested in here is the S parameters of the overall device. So this waveguide is 100 microns long, and it's between these two grating couplers. So we're effectively shining light in a fiber in one and collecting it out of fiber out of the second one. So if we go to our optical network analyzer, we can start looking at the different results. So this is actually the S11 results, so the reflected light. Again, I'm going to switch to looking at the absolute value. And here what you see is that we have reflections which are, maybe if I put it in power for 1 second, we have reflections of around 1%, and but there's a lot of ripple on these reflections. And if I add in the transmission S21 here, and again I'll flip to the power. You can see that we get a reasonable transmission through this device. It's right, we're almost up to 20%, which is not bad considering we've come in and back out of a grating coupler, but we also have this ripple on this device. And the reason for this ripple is that we've effectively created a Fabry-Perot resonator in this between these two grating couplers, which each provide a certain amount of reflection, and it's this resonator which is leading to this ripple. And so the space between these ripples is related to the length of the waveguide, and if we increase the length of the waveguide, we would find that the space between the ripples, the free spectral range, of course, is reduced. And of course, with interconnect, we can look at not just the magnitude of the S parameters, which is shown here. We can actually also look at the phase. Again, you know, here the phase for S21 is fairly linear as we expect. Something is going on with S11, sort of changing between two regimes of which dominate the reflection here, and then. In terms of the power, this is the curve that I showed you. I've just relabeled the axes and plotted as a function of wavelength. Here we see the reflection and the transmission. So we can see already that these reflections, which actually in terms of power from the grating coupler are relatively low, sort of on the percent or less, do have some important consequences. Even on the transmission side, we're seeing the effect of all these ripples. And so whether or not this is important depends on what what you're trying to do with your particular circuit. But it may be that, for example, we'd want to go back to the original design and start to design to reduce the reflections as well as to increase the transmission. And if the reflections were an important specification, we could have created a figure of merit that took both of those effects into account and then rerun the optimization for that purpose. And of course, in terms of simulation of circuits, we don't want to just simulate a grating coupler, waveguide, and a grating coupler. With interconnect, we want to be looking at larger scale circuits like this optical transceiver. This is a 2-channel optical transceiver, and we see that in this design, we see grating couplers being used to bring external light onto the chip, and of course, the grating couplers are used to output from the transmitter side into the fiber, and then to bring the light back onto the chip on the receiver side. So grating couplers can be an important part of these larger scale circuits, and you can imagine that if you have reflections occurring at various different points, that could have an impact on the overall performance of the circuit. In this case, could be something that would limit the ultimate transmission speed that's possible. So I have a few conclusions at the end of the webinar. As I pointed out at the beginning, the grating coupler can have many different advantages. We can place them anywhere on the chip, and cleaving is not necessary. But of course, they do have some disadvantages. The bandwidth is more limited than end-fire coupling. We can have higher reflections. But these limitations can be overcome for many applications with suitable design tools. If you have certain requirements in bandwidth, certain requirements in reflection, then we can work at optimizing the designs to meet those specifications. And using interconnect, we can determine actually what the specifications need to be in terms of their impact on the overall circuit performance. The grating couplers generally are challenging to simulate. These structures are very large in 3D, and yet they're also high index contrast structures that require a method like FDTD. There's also many analysis challenges. It's not really sufficient to just figure out how much light is transmitting through a certain surface. We actually need to know how much light is propagating in a particular mode, and in this case the fundamental mode. So to do that we use modal expansion, and when you consider fibers that are rotated, you actually need to start looking at rotated modal expansion, which is a pretty complex type of analysis. And then the parameter extraction for inclusion in the circuit and system simulation is not trivial, but once you can do modal expansion, it does become much easier. So different solutions to these simulation challenges. What I've shown is how we can start with very simple designs, so really back of the envelope designs using slab waveguide properties, and we get those slab waveguide properties almost instantly with the eigenmode solver and mode solutions. We can then use 2D FDTD and the 2.5D propagator and mode solutions to optimize different aspects of the design, the grating coupler itself, and also the taper design. We can put those together in 3D FDTD for final simulations, and the simulations are still on the order of 10 minutes or less on a decent workstation, so there is still a lot of possibility to do optimization, a final stage of optimization in 3D as well as in 2D. And then parameter extraction, we use these modal expansion monitors to extract the S parameters, and we can do this for angled fibers, and that allows us to include these results in interconnect simulations where we can do these frequency domain network analyzer simulations that allow us to look at the S parameters of the overall circuit. And we can actually even use this information to do time domain simulations and look at signal integrity analysis as well. So I've come to the end of the webinar, so now I'll open up the floor to questions and answers, and I'd like to thank everyone for attending.